Well, hello. My name is Scott Grizzard. This is Calculus 2020, the quiz review 11B, the 5 p.m. edition. And there is no one, and I mean no one, in my classroom right now. So I guess everybody's watching the election results, and I'm not very interesting. I just can't get into watching the election results on TV. It's kind of like watching the Yankees play the Red Sox. I kind of want them both to lose. So, it's not very fascinating to me, but okay. I'll just go ahead and I'll start reviewing the quiz. And if somebody comes in to ask questions, well, they can ask questions. So, okay. Maybe I'll, not be teaching this afternoon after this. So, let's just get started. So this was the quiz, and it was asking you to do an optimization problem where I wanted employee parking with 300 square feet. And 3 of the sides were visible to the patrons, so the fair would use themed fence. However, this north side here cannot be seen by the patrons. So on the north side, we're just going to use chain link fence. And which is 1/2 the cost. So this is kind of the setup here. And then I kind of want to know the least expensive way to set this up. So I'm producing A, and my cost is kind of this modified perimeter. Okay? Now, it's a common mistake to assign variables too early, right? You need to draw a picture and kind of work out what's being produced and what the cost is, the functions type of R, before you really assign variables to the things. But, so if you assign variables too early, you tend to assign these things to the wrong thing. So the variables really come from production, right? So I've got this area, my production function is area, which equals W times L, which is fixed at 300. And then I have a cost function, right? And then so I label these things for my production, W and L. And then I have a cost function that's, well, I need to pay for that fence, that fence, that fence at full price. And then I get a discount on that one. That's half the cost. So whatever the cost function is, it's going to be L plus W plus 1/2 W. Okay. I would ask how we feel about that 1 to 5, but no one is here to answer, so that's okay. If you are 1 to 5 in Twitch, you may say something there. Oh, there is someone watching. So, and then, so what I'm going to do here is I'm going to minimize C given the area. Okay, so remember on the first problem that I did on the lecture, I was maximizing area given some cost, right? So I want to find out which one's fixed and which one's moving here. So I could do this thing here, right? I could make a little chart of all the variables, right? There's A, there's L, there's W, fixed moves, drives, moves, that kind of thing. And I want to maximize this. Okay. Now, if you accidentally assign a bunch of variables too early, you'll wind up with something like this, which is okay, right? I mean, I could assign the themed fence to be T and the half-priced fence to be H. Right, and then I give a length and a length, and then I give a W, and it so I can do this. This is more complicated. This is cleaner. And then there's this L and the W, which I just kind of assigned, and it doesn't matter which one is which. You could have this be L, and you could have this be W. I advise you not to use X and Y. This is a little tip. Try not to use X and Y's because you sometimes get confused with graphs. I'll just add that as a little tip. Try not to use X and Y as variables to avoid graph confusion. All right. That's just a little tip. Okay. So I've got this these things here, and what I'm going to do, I don't know why I did that. So I've got my two equations here after looking at this, and I'm going to minimize C given A. So what I'm going to do is this kind of solve and sub from my constraint, right? I've got W times L equals 300. That means that L is going to be 300 over W, right? I sub in the thing that's fixed, and I get this. And then I take the thing that's fixed, and I sub it in for my cost, and I get 300W over 300W plus W time plus W plus W over 2, which I simplify to 600 over W plus W. And I could actually simplify this further if I wanted to. So this is really 2 over 2W. So this is really 3 halves over W. You could simplify that in advance. Right. And then what I want to do is I want to just talk about the endpoints. Okay, so remember when I do these maximization, minimization, find the absolute max, and I am on Blackboard. Okay, so apparently there are people talking to me. It's just that I'm on Blackboard, and for some reason, I'm in Blackboard Collaborate Ultra. This explains the problem, is that apparently... Okay, well, let's try to fix this. Maybe I did. So apparently there's an issue with Blackboard Collaborate Ultra. Hey, look at that. I do have students. Okay, I don't know what Blackboard Collaborate Ultra was doing there. Maybe I joined the wrong session. With admin privileges, maybe it's got all the section things. Okay, so let me get up here on this. There. Okay, well, I don't know what was going over there. Okay, so 1 to 5, how do we feel about where I am? If you've been watching on Twitch. Okay, well, now everything's so far. 1, 2, 3, 4, 5. Okay, so now I have polling. I have students. I thought you all were just playing hooky, and I was going to get to go home after doing the quiz. I was kind of all excited. Okay, so I guess I need to start over a little bit. What I did was I drew my thing out so that I had cheap, theme. I know that I've got this 300 square foot thing. I put my L's and my W's there. I got my L's and my W's from my production. So I'm producing A. And that's where I got my L's and my W's. And then I have this cost thing, L plus W plus 1/2 W. All right. So again, I said don't try not to use X and Y. It doesn't matter if you put L here and W here. That's fine. Also, don't label things too early. And it's a common mistake to try to label things off the cost. It's usually better to label things off the production. Okay. That's just a thing. These this is just another tip. Usually it is better to label things off the production. Okay, so if we think about the thing that's being produced is area, and it costs something to produce. Okay, so I'm going to, my production function is W times L, which is area, which is 300, right? And I can make my little table here if I want to. A is area, it's fixed. L is length, it moves. Width drives. It doesn't matter which one drives and which one moves. And cost moves. Okay? So 1 to 5 now. How do we feel about the news so far? Okay. All right, so what I did was I kind of just solved and subbed. I'm minimizing C given A. So I took my production, right? This was the thing that was fixed. And I subbed in here to solve for one of the variables. And then I took this and I plugged it in here to get one big equation to take the derivative of. Okay? And then I want to kind of reason about the endpoints. Well, as if W gets bigger, C is going to shoot off to infinity. And the same thing happens for L. This should actually be labeled W because I'm using W here. So I get this kind of graph idea of going on here, right? Here's my thought on the endpoints. It's going to look something like this. Right? As W goes to 0, C goes to infinity, and likewise, as W goes to infinity, C goes to infinity. Okay? So how do we feel about kind of what's going on with the endpoints, 1 to 5? Right. That's just kind of my reasoning on that, right? I just kind of take the limits and, that's what I get. And I don't really need to make it, a big deal. It's just like kind of real life reasoning, right? I can't have negative fence. So I'm just okay with no negative fence, right? Okay. So what I'm going to do is I'm going to minimize C by taking the derivative. So when I take the derivative, let's just make this 3/2 because that's what I did. I changed this equation here to 3/2. So when I take the derivative, I'm going to wind up with -1 because this is a 1 here. There's a -1 here. So I pull down that negative and I get -1 times 600W to the -2 plus 3/2. And then I rearrange this. 3/2 equal minus 600 over W squared. And I set it equal to 0. Okay? So how do we feel about that? So I'm doing the exact same thing I did before. And on this test, you can think of the idea, we had, on test 2, it was when in doubt, take a derivative. On test 3, it's when in doubt, take a derivative and set it equal to 0. Okay? So how do we feel about, doing the derivative for critical values? 1 to 5. Okay. Now, once I have that 20W, I'm going to go ahead and solve for L. All right. Now, I need to check to make sure that I have a min. Now, there are three ways to do this. The first is to make an endpoint argument. And for this, a drawing is always nice. Okay? The second thing I could do is I could sample the first derivative, or the third thing I could do was take the second derivative and see if I could pull it off concavity. Okay? So there are three ways to do this step. Okay? Option one is to make this argument. Okay? So if I wanted to do option one, here's how I would do option one. Okay, this is the endpoint argument. It's an argument. It's not an argument. Okay, I draw me a little graph here. I do this, and I do something like that. I put W down here. I put C. I say something, only positive values make sense as W goes to 0. I would need infinity length. So cost goes to infinity, and as W goes to infinity, C also goes to infinity. Okay. Since there is only one endpoint, since there is only one critical value, I found them in. Okay. So how do we feel kind of making that kind of argument 1 to 5? Again, you don't have to do that. There's mathier ways to do it. Mathier ways to do it. But you can do it this way. And it's actually a very good way. Making an argument about the endpoints. I felt so sad and alone when I thought you guys had skipped my class. It was just, I was so happy to find out it was because I had joined the wrong session or something weird, which is very strange. Apparently there must be some kind of like master session or something, because I could have sworn I clicked on today's. Anyway. Okay, so I can make an argument for endpoints, right? I've got one critical value, the thing's shooting off to infinity on either side. I got them in. Okay. I could also check for a min by doing the first derivative thing. So this is option 2. And to do that, what I'm going to do is I'm going to put 20 over here where W is. Okay. I'm going to put a sample problem here, because remember, this is 0, 20. And this right here is 20 infinity. So I'm going to pull some sample things. Well, 10 would be a nice thing to square. And then, I'm going to have 600 on the top. So, things that are multiples of 10 would be nice to divide. So I'm going to go ahead and I'm going to throw 10 here and 30 here. So I take C prime of 10. And remember, I actually don't care about the value. I only care about its sign. So this thing, right, I've got 10 squared here. I'm going to divide out 100. I wind up with 3 over 2 minus 6, and that's smaller than 0. Whereas if I do this one, I'm going to wind up with a 300 here. So I just, I divided out the hundreds. The 300 here. I'm going to wind up with a 900 here. I divide out the hundreds. That's 6 over 9, which is, 2 over 3. And I don't care about anything about 6 over 9, except for the fact that that this right here is not as big as that, right? So I'm subtracting a smaller number, right? This is bigger than 1. This is smaller than 1. I'm going to wind up with a positive number. And that's all I care about. I don't care about what the number is exactly. So I've got a negative here and a positive here. So I will go down and then I went up. That means I have a min. Okay. So 1 to 5, how do we feel about option B, option 2 there? This is called the first derivative test. Okay. So I pick which one I want to do. Here what I did was option 2 in the purple. But again, I could have done any of these things, right? So I could have done option 1. I could have done, now option 3 is to look at the concavity of the thing. So as you can see here, if a function is concave up at a point where the derivative is 0, that means I've got a min, right? I'm at the lowest point. Okay, well, so that's fine. So what I do is I take the second derivative, which means I take the first derivative of the derivative. Right? I take the derivative of the derivative. I wind up with a 0. Now, because I have a negative 2 up here, I'm going to wind up with negative 2 times 600 times w to the negative 3. So the negatives cancel. I wind up with 2 times 600 over w cubed. Again, I don't actually care what the number is. I only care about the fact that it's bigger than 0. So I have C is concave up and I have a min. Okay? So how do we feel there about option 3? Okay. All right. And then what I'm going to do is I'm going to kind of put it all together and then make sure I answered the question, right? So I said that the least expensive option will be L equals 15, W equals 20. What's the total cost? I don't really know. Because it didn't give me a money amount. Something's wrong here. I should be able to do that. Let's go look at what the question said. Oh, what is the least expensive way to set up the parking lot? And how many feet of themed fence and how many feet of chain link fence do I need? Oh, they don't actually want me to tell me what the total cost is. They want me to say how much of this and how much of that. Well, that I can say. I come back here and I say what I want. I'm going to use 2 times 15 plus 20, right? Because this was a theme, this was a theme, this was a theme. LWL. So my dimensions are going to be 15 feet by 20 feet. Those are my kind of dimensions. I'm going to do 20 times 2 times 15, which is 30, plus 20, 50. I need 50 feet of theme fence, and I need 20 feet of chain link fence, and that's the cheapest way to do it. Okay? It didn't ask me for what the actual cost was. It just asked me, what's the cheapest way to do it? Okay. So 1 to 5, how do we feel about that? Kind of just putting it together. There we go. Okay. So again, I want to go back, just kind of read. Now, we are going to do a lot more of these problems. So next week's problem set is going to be focused almost exclusively on these problems. Actually, it is exclusively on these problems, right? Next week's problem set, I'm going to give you a bunch of these, and we're going to have some fun. And I'm going to be asking you different things. But the point is that you can kind of pull what you need to do off these, and there's a lot of ways to do them, right? It's not like, unrelated rates or all these other things, right? There's kind of a method to it that's permanent, right? There's some kind of boom, 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 boom. I mean, there's multiple ways to do it, but I'm telling you, you want to do it this way. Boom, 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 boom. Row, you bastards, right? Not this time. There's not really a method that I just say, follow this step, then follow this step, because these problems can be a little different. If you open your book to this section, I think it's, 4.5? I don't want to show the ebook on the thing, but if you open this book to the section and you flip down there, 4.5, and you flip to these kind of last problems, of course you're doing it on the ebook, like 51 is Snell's law, I think. Yeah. So it's about light bending. And there's all these other problems like that. So it's these things are common in physics. They're common in engineering. They're really common in economics. So there's kind of a flavor that you have to get. But they're all kind of like a theme, I'm minimizing or I'm maximizing. So they all kind of have the same middle, but they may have different beginnings and different ends, right? So it's not really something I can just like do this, do that, do that. You have to kind of play with the beginning and play with the end. The middles are usually the same. It's kind of the opposite of chess, in a sense, right? So every kind of one, you're taking a derivative, setting it equal to 0, finding out where those things, checking the endpoints. Okay, but the beginning and the end can be different depending on the particular problem. So there's more of a coach thing that has to happen here. You have to ask questions. And you kind of have to, come to office hours, do them in groups, or talk to tutors until you kind of go, oh, I got it. And they're hard in the sense that the beginnings are kind of always different. All right. Are there any questions about that? So 1 to 5, how do we feel about the fact that you kind of have to do coaching, not teaching on this, right? I can't just show you how to do it. You kind of have to play with it and come ask questions. So 1 to 5, how do we feel about this idea that this is really a coaching scenario? It's more of coaching and not as much teaching. So you kind of have to come ask questions if you get stuck on one. And as I said, I'm going to give you a whole bunch of them next week. Well, not a whole bunch, but, kind of like the related rates problem set where I gave you a bunch and said pick 3. It's going to be something like that. Any questions? I kind of moved through that kind of quickly. All right. Let's look at this. Now, here's one of those things that I really hate, but I'm going to show you because people like to do it. And, one of the things is I don't always have the greatest input right now on what should be on the test because because you guys did like awesome on the second test and awesome, on the first test compared to the other sections. You did kind of awesome. Yes, there was a section that did better. But there were a lot of sections that didn't, right? So, we're kind of second best right now. And there's only so much that when I complain about things like this, they actually care. Because they're like, your students will get it anyway, right? And they're all like worried about what their students are going to get. So, there's only so much effect I can have. And this is one of those common things that annoys me. And that is there's another condition stuck in the preamble. There's really 9 conditions here. Okay? And one of them's been stuck in the preamble. So 1 to 5, how do we feel about that idea that there's a hidden condition? Stop. There it goes. They just stuck it in the preamble. You know, that's not nice. I don't like that. I think that's mean. Okay. But this happens. Like, you get differentiable up there. You could get other things defined everywhere. You can just kind of have things thrown in the preamble. All right, so let's look at these conditions and see what we've got here. We've got that negative infinity, negative 3 is on the graph. Let's just slide down there to negative infinity on the x, negative 3 there. I'm just going to stick an arrow right there. I've got increasing on negative infinity, negative 2. So from negative infinity to negative 2, I have to be getting bigger. F prime is less than 0 for x in negative 2 to 0. So here I have to be getting smaller. F is concave down from negative 3 to 0. F prime of 1 does not exist, but it's continuous. That means a kink. The limit as x goes to infinity of f of x equals infinity. That means infinity, infinity is on the graph. So I'm just going to go ahead and put that there. Okay, this one's tricky. What does it mean for f double prime to equal 0 on 1, 3? Here's the question. Is that a point or an interval? And how do I tell the difference? This is the second way that these problems can annoy. What does that word on mean? Okay, so let's take a vote. Vote for f double prime equals 0 on 1, 3. 1, 3 is point, or 1, 3 is interval. Okay, so let's do it. Let's see, 1, 3 point, and 1, 3 interval. I really need a peer leader for this, right? So she can do or he can do this. I like how Laura and Kiera tag team. What have we got for votes? Time to vote. Come on. It's an election. Respond to peer pressure. Vote, vote, vote. All right, we just passed 50% turnout. Okay. I don't know if it'll let you. We take you off to federal jail. Trump applauds you. I don't know. Okay. So, the answer that it's thinking about is in that word on. Okay. So this word on is the key. If you say at means a point, on means interval. And that's annoying. This is one of the reasons why I like to use angle braces for my points and parentheses for my intervals, right? Because this is, because I have it in parentheses, it tells me, oh, interval. But, you know, the standard is, you know, this is becoming the standard, but it's not there yet. So the textbooks and stuff like that still have these parentheses for points and parentheses for intervals. I find that hugely confusing. But that's what it is. This word on is the thing that tells you that f double prime of 0 is an interval, as equals 0 on that interval. Okay, so how do we feel about that? This is just kind of a heads up, just in case it happens. I don't know if it will, but that's just kind of the things that can happen. The word on means an interval and at means a point. Now, what does it mean for f double prime of x equals 0? What does that mean? It means my slope is not changing. It means I have a line. So from x equals 1 to x equals 3, those were the interval, right? This function has to be a line. And then f double prime is less than 0 for x greater than 3. Concave down. Okay, so how do we feel about what the conditions mean, 1 to 5? Okay. All right, now I'm going to connect the dots. Now, the tricky one is right here. I've got overlapping conditions here, so I'm going to deal with that first. I'm going up, and then I'm going down, and I've got concavity. So I'm going to deal with that first. I'm going to go above, I'm going to come up, and I'm just going to do a little max here, and then I'm going to come back down. I'm going to make sure I'm actually concave down, so let's make it a little bit more strictly concave down. All right, now I'm here. I've got a kink that goes into a line. Let's see. Now, I could just have it go like straight this way, but if I do that, I can get away with that. That'll work. But I've got this concavity condition. Let's deal with that first. All right, so I want this thing to be strictly concave down here, but still go off to infinity. Something like this will do it. Oops, that's heading into my line territory. So how do we feel about this idea that I can have something concave down, but still have it be increasing forever? Okay, that's a tough one. 1 to 5, this idea that I can have concave down, but increasing forever. How do we feel about that idea? I don't need to go down when I go concave down. I don't have to have it be decreasing. I just have to have the tangent lines run above the curve. Right? That's all that has to happen. Okay. Can someone give me an example of such a function where it's concave down, but increasing forever? The limit is infinity. The limit is infinity, but it's always concave down. Who's got an example of such a function? We've actually seen a few. We've seen them on quizzes. All right, remember that function that I asked you to do for linearization, where I asked you to do the cube root of x? That's an example of such a function. Okay, if I look over here, whenever I do a tangent line, it's going to run above the curve. But this function actually goes off to infinity. Is everyone on board with that? One to 5, how do we feel about this idea? Okay, can someone give me an example of another function where the limit is infinity, but it's always concave down? How about the natural log? This thing is always concave down, right? But as I go, it will get to infinity. It will get to infinity. It just gets to infinity very, very slowly. Okay? It will get there. You know, in a kind of Cockney way. Is that a Cockney accent? The instead of an e. It will get there. But it just takes a while. A long while. Very slow. Okay. All right, I need this to be a line. I need this to kind of connect the dots. So I'm going to just take a line. I'm going to make a line. I'm going to do this. Oops. I'm actually going to want them to connect. By the way, your student ID is the best ruler in the world, or straight edge in the world for this. It works very nicely. Okay. So now it's a line, and then I'll just kind of label stuff for the grader. Oh, let's see. I've got horizontal asymptote over here. Give me the 0 degrees. Give me the 0 degrees. There you go. I'll just label things for the grader. So I've got a horizontal asymptote. That should be just slightly higher. Yep, there we go. I have a max here. That gives me that derivative equals 0 type thing. Kind of up and down. This is concave. Here I have a kink. Here it's a line. How do we feel about that? Just kind of putting that together, 1 to 5. Okay. And then, of course, I need to check to make sure I got everything. Is my limit as x goes to negative infinity of f of x equal to negative 3? Yes. Am I increasing from negative infinity to negative 2? Yes. Am I decreasing from negative 2? So my slope's negative from negative 2 to 0? Yes. Do I have a kink at x equals 1? Yes. Do I go off to infinity? Yes. Do I have a line here between 1 and 3? Yes. Am I concave down for x greater than 3? Yes. Okay, so I've got it. And then am I continuous? Got it. Okay, and then do I pass my vertical line test? Yep. Okay. I'm going to give you, these graphs are really good problems. So I'm putting, I've got the stuff. I mean, people are already, we got a draft of the problem list and the study guide, and people are already posting it. So I guess we're allowed to post it. So I'll post what I've got for the test. But these graphing problems are nice. Sometimes they're a little tricky. This idea that I don't have to, oh shoot, you're looking at the wrong. I'm sorry. I don't have the. I've got the tablet thing up. So yeah, I did the vertical line test. I checked everything to make sure it worked, and then I did the vertical line test. Sorry about that. I left the screen on the graph, the other graph. So this idea that these tangent lines can run above, but I don't have to go back down. Is kind of the thing that you needed to get out of this. And then the idea of the lines and all that. Okay. So that's it. Any questions? Okay. So what I'm going to do is I'm going to stop the stream and I'm going to talk about the problem set for just a moment. No, it does not have to be a horizontal line. Any line will do, right? If it's a horizontal line, that means that it's the first derivative is 0. Second derivative is 0, so it'll work. But the issue was that the second derivative had to be 0. So any line will have a second derivative of 0, right? X plus 3. I take one derivative, I get 1. I take another derivative, I get 0. Okay. All right.